Howdy. We're going to talk today about motion along a line and how integration can be used to find position or velocity given a velocity or an acceleration. And so I want to begin by reviewing what we talked about in class last Thursday. And that is that if you know the derivative of a function, then you can find the original function that it came from. And if you further know one point on the curve, then you can find the particular constant of integration that is that pops out of the antiderivative. So let's review the process here. We have a derivative dy dx is equal to negative 1 over x squared, and we're supposed to find the y whence it came. So we would write that y is equal to the integral of the derivative of y. Now this integration here needs a little bit of rewriting. I'm going to bring the negative 1 to the outside and write the quotient as x to the minus 2 power. And now we have a straightforward power rule. Add 1 to the power, getting negative 1, and divide by the new power, plus the obligatory constant c. And when you clean up a little bit, then your negative 1's cancel out, and you can rewrite that as 1 over x plus c. The c comes about because antiderivatives are going to be of negative 1 over x squared are going to be equal to one another within a constant. But if we have an initial condition, a specific point that we know on the curve, then we can use that to find the value of c by plugging in. Since y is equal to 1 over x plus c, and we know that when x is 1, y is 3, then we can plug in those values and get that c is equal to 2. So that our particular solution is y equals 1 over x plus 2. How would I check this? Well, I would check to make sure that it has the right value at x equals 1. So when I plug in x equals 1, I should get 3. Let's check that. 1 over 1 plus 2 equals 3. Check. And also y prime, or dy dx, should give me the correct result. And sure enough, when I take the derivative, I get negative 1 over x squared. And so because the derivative is correct and the initial condition is satisfied, we say that we have found the unique solution to our original problem here. Well, there's that. Sometimes these problems can be a little more sophisticated. Here's one where we're given the second derivative of a function. We're given that f double prime of x is equal to x to the negative 3 halves power. And we are given two pieces of information, two initial conditions. One of them is that f prime of 1 is equal to 2, and the other is that f of 9 is equal to negative 4. What does this do for us? Well, if you think about it, f double prime is the derivative of f prime. So that if I integrate f double prime, what I am going to get is f prime plus c, just like that. Aha! So this allows me to integrate f double prime, the original second derivative that was given to me, and call that f prime of x. Let's see here. Add 1 to the power, getting x to the minus 1 half, and divide by the new power. Clean it all up and get negative 2 x to the minus 1 half plus c. And this is f prime, or the antiderivative of f double prime. Now to find the value of c, then we appeal to the initial condition for f prime. when x is 1, then f prime is equal to 2. And so I can substitute just like so. When x is 1, f prime is equal to 2. Or in other words, 2 is equal to negative 2 plus c, since 1 to the negative 1/2 power is 1. And c is therefore 4. And I now have an expression for f prime of x. My particular f prime of x that satisfies the initial condition is negative 2x to the negative 1/2 plus the value of c that I found. So one integration step takes me backwards one derivative. I started at f double prime, I integrated, and I landed at f prime. Well, you know where this is going. If I integrate again, then I'm going to get f directly. And in fact, that's exactly what we do. Since I have f prime is equal to this, I can say that f of x is the antiderivative of f prime. And now we can use our integral properties to split up the integral into two smaller and easier integrals to work with. Let's see here. Add 1 to the power, negative 1/2 plus 1 is positive 1/2. Divide by the new power, plus the function whose derivative is 4 is 4x, plus the obligatory constant c. Let's clean that up a little bit, because negative 2 divided by 1/2 is the same as negative 2 times 2. And now to find the value of c, we appeal to our initial condition, which is f of 9 is equal to negative 4. Let's plug that in. When x is 9, then f is negative 4, so that I get negative 4 is equal to, let's see here, that's going to be negative 4 times 3 plus 36 plus c, which is 24 plus c, so that c is negative 28. And we now have our final solution for f, which is negative 4x to the 1/2 plus 4x minus 28. Likewise, I would check this guy by making sure that it has the right initial condition, that f of 9 does equal negative 4. Let's plug in and verify that. It's going to be negative 4 times 9 to the 1/2 plus 4 times 9 minus 28. And that's negative 4 times 3 plus 36 minus 28. Or negative 12 plus 8, which is negative 4. Hey, that checks out. We're also going to make sure that we get the right value of f prime. Going all the way back here, when x is 1, f prime should be 2. Let's check that. So here's my f of x. My f prime should be equal to negative 4 times 1/2 x to the minus 1/2 plus 4, and the negative 28 disappears. So the f prime of 1 is negative 2 times 1 to the minus 1/2 plus 4, which is equal to 2. Is that a match? Why, yes it is. And then finally, we'll make sure it has the right f double prime. We go back, we go all the way back down here, and take our second derivative. Prime of x is equal to the derivative of negative 2x to the minus 1/2 plus 4, which is going to be negative 2 times negative 1/2 x to the minus 3/2 plus nothing. And these guys cancel, giving me x to the minus 3/2. And we have a match. So this was a more elaborate example, but it shows you that if we are given a second derivative of f, we can find it with 2 integration steps. And of course, we need two different initial conditions, one for f prime and one for f. Pause for just a minute and see if you can summarize what this lesson has been about so far. If you need to go back and take another listen to it, then feel free and come back when you're ready. Welcome back. We're going to be using the idea of antiderivatives to do something very, very simple. And that is, we're going to be analyzing motion along a line with the information that we already know. Since velocity we already know is the first derivative of position, therefore position is the antiderivative of velocity. And since acceleration is the first derivative of velocity, then velocity is the antiderivative of acceleration. That's the big idea. Now let's see how this works out. For example, suppose I know that the acceleration of an object is given by 3 sine t. And I also know that the velocity at time 0 is equal to 2. Now, find the velocity for any time t. Notice that what's given to me is the acceleration at any time, the rate of change of velocity, and also a single initial condition. And based on that, that should be enough to find the velocity for all time. So, how do we proceed? We proceed by remembering that acceleration is the derivative of velocity, so velocity is the antiderivative of acceleration. I write this step here just to remind you of the logic. In practice, I probably wouldn't write that step out. Instead, I would just write velocity is the antiderivative of the acceleration, just like that. And now we can use a little bit of constant multiple rule. Pull our 3 to the outside. And we remember what function has a derivative of sine? Ah, yes, negative cosine. Plus c. A little bit of cleanup here. Just like that. Now, having found the velocity, we notice that the velocity depends upon a constant of integration, reflecting the initial condition that was given to us, v of 0 equals 2. So I can now use that initial condition, v of 0 is equal to 2, by plugging in 0 for t and 2 for v. And the cosine of 0 is exactly what you think it is. It's 1. So that c is equal to 5. And this allows us to find the particular velocity, negative 3 cosine t plus 5, that satisfies both the acceleration and the initial condition. Let's just check that. We check that the acceleration is correct by taking the derivative of the velocity. That gives me negative 3 times negative sine t plus nothing, or 3 sine t. And that's exactly what we wanted. And we also check that v of 0 is equal to negative 3 cosine 0 plus 5, or negative 3 times 1 plus 5, which is equal to 2. And that also is exactly what we wanted. So the process of finding velocity from acceleration is simply a process of finding an antiderivative and using an initial velocity as the initial condition. We can do a little bit more with this, actually, because here, in this problem, we are given acceleration. We are asked to use that acceleration along with some initial conditions to find the time for which x of t is equal to 0. Well, if I'm going to do that, then I'm going to need to find an expression for x of t. And what I am given is the acceleration. And this acceleration, because of the way that it's written here, is considered to be a constant acceleration for all time. In other words, I would write a of t is equal to negative 32 feet per second squared. So what can I do with this? Well, because I am given the acceleration, a of t, I can use that to find the velocity, just as we did in the previous problem. I can say that velocity is equal to the antiderivative of the acceleration. Looking for the function whose derivative is negative 32, and that would be negative 32t plus c. This is now where the initial condition comes into play. My velocity when t is equal to 0 is 16. And that's the same as negative 32 times 0 plus c. So that my constant of integration is 16. And this gives me an expression for the velocity for all times. Just like this. Those of you who are in physics will probably recognize the equation V equals V0 plus AT, sitting right there. And where this equation comes from is from integrating a constant acceleration. Now that I have the velocity, I can use that to find the position with another antiderivative. X of t is going to be the integral of the velocity dt. And we can use integral properties to divide this up into two integrals. Just like so. And the first integral, add 1 to the power, divide by the new power. And second integral, 16 times t plus c, which gives me negative 16t squared plus 16t plus c. Since this c here is different from this c right here, sometimes you'll see books write this as c1 to distinguish the two. And we can do that. Now I can use the initial condition that x of 0 is equal to 32 by plugging in. So x of 0 is equal to 32 is equal to negative 16 times 0 squared plus 16 times 0 plus c1. Or in other words, c1 is 32. And therefore, I finally have my expression x of t is negative 16t squared plus 16t plus 32. And again, if you've been in physics, you'll probably recognize the equation x equals 1/2 at squared plus v0t plus x0. And that equation comes about by integrating the equation for velocity. Well, we're finally ready to answer the question. We want the time for which x of t is equal to 0. And so we set our expression equal to 0, and we remember that factoring is our friend. So we're going to factor out, first of all, a negative 16 from this expression. And then factor it as t minus 2 and t plus 1, so that we get negative 16, so that we get either t minus 2 is equal to 0, or t plus 1 equals 0, or in other words, t equals 2, or t is equal to negative 1. Probably the domain of the problem would restrict this answer here, but because the domain was not supplied, we don't want to be too hasty. So, moral of the story. We began with an acceleration, which happened to be constant, and we integrated that to find velocity, and then again to find position. And then finally, we answered the question by setting the position equal to 0 and solving for the particular times. I'd like to take a look at a couple of word problems to see how this works out in practice. First of all, a large category of word problems fall into the category of free fall problems. where objects are experiencing only the force of gravity and no other forces. And it is a remarkable thing about objects experiencing only the force of gravity that they all accelerate at the same rate. This remarkable fact was first discovered by Galileo and then quantified by Isaac Newton. And what he found was that for objects near the Earth, the acceleration of those objects is negative 32 feet per second squared. Or if you're in physics, the more familiar, negative 9.80 meters per second squared. This value is peculiar to the Earth. If you are doing physics on the Moon or on Jupiter or on Venus, then you will have a different value for the free fall acceleration, which is often given the symbol G for gravity. Here's how this works out in practice. An object is dropped from a, sorry about the spelling there, from a balloon that is stationary at 1,600 feet above the ground. Express its height above the ground as a function of time t. How long does it take the object to reach the ground? At first, it seems like we're not given enough information. The only thing we're given is that it is 1,600 feet above the ground. But actually, a little bit more is given. Let's draw. Here's our balloon, and here's our object. And we know that the object is 1,600 feet above the ground. Probably the best way to represent that is with coordinates, like so. The reason I would do this, put the 0 here, is that we're told to express its height above the ground as a function of t. And so we want height to be 0 on the ground. But we're told a couple of other things. First of all, we're told that the balloon is stationary and that the object is dropped from it. And what that means is that our object is going to have an initial velocity of 0. When the problem starts, the object is not moving. So that's the first thing. And then the second thing that is in the background that needs to be understood for all of these problems is that since the object is being dropped near the surface of the Earth, it is therefore going to experience a constant acceleration of negative 32 feet per second squared. This information is not stated in the problem, but it is implied because the object is being dropped near the surface of the Earth. So, armed with this information, we're now ready to express its height above the ground, which is its position, by doing some antiderivatives. Since I have the acceleration, I can say that the velocity is the antiderivative of the acceleration, which gives me negative 32t plus a constant. And I can find that constant with my initial condition that the object is stationary. Since the object is stationary, the constant of integration is 0, and I now have that the velocity of the object is negative 32t plus nothing. What about the height of the object? Well, you can call this y of t, and that's going to be the antiderivative of the velocity. Using constant multiple rule, we get this. And using the power rule, add 1 to the power, divide by the new power, plus the obligatory constant c. And here, we have an initial condition that is stated right there. When the problem starts, the object is 1,600 feet above the ground. We could write that initial condition as y of 0 is equal to 1,600. So that when we plug in for our initial condition, 1,600 is equal to, let's see here, negative 32 divided by 2 is negative 16. And C1 is equal to 1,600. And this gives me now y of t, the height, is equal to negative 16t squared plus 1,600. And so this is the answer to the first question. The height above the ground at any time t will be negative 16t squared plus 1,600. The second question is, how long does it take the object to reach the ground? The object is going to reach the ground when its height is 0. And so therefore, we can set the height equal to 0. And solve. I kind of like solving by factoring. Factor out a negative 16. And factor into t minus 10 and t plus 10. This gives me t is equal to 10 as a solution, or t is equal to negative 10 as a solution. Since the problem starts at t equals 0, we actually reject t equals negative 10 as a solution. And we have 10 seconds to reach the ground. Stop and visualize this problem for just a minute. What we're doing is taking this object, which is 1/3 of a mile above the ground, and we are dropping it and counting 1, 2, all the way to 10, and it finally hits. It's pretty remarkable. Let's look at one final problem here. The ball is released from rest and rolls down an inclined plane with a constant acceleration. In 4 seconds, the ball travels 100 centimeters. What is its acceleration in centimeters per second? Well, what do we know here? Here, we're told that the ball is released from rest. This tells us that when time is 0, when the problem starts, the velocity is 0 also. Second of all, we're told that it rolls with constant acceleration. They don't tell us what number that acceleration is, so we're going to call it something like a. We know that it is a constant, however, and that's going to be very helpful to us. And then finally, we're told that in 4 seconds, the ball travels 100 centimeters. So if we're picturing or visualizing this, the ball is starting right here. We'll call this x equals 0. In fact, we'll say x of 0 is equal to 0. When the problem starts, we haven't traveled any distance. And now after 4 seconds, x of 4 is equal to 100. And this is the way that we can translate this information into the problem. And now we are asked, what is that acceleration, which is a, in centimeters per second per second? So how are we going to proceed? We're going to do it in a manner very similar to the last problem, but this time we don't know what a is. And that's actually not a problem at all. We're simply going to say that the velocity as a function of t is the antiderivative of the acceleration, which is a constant. And because it is a constant, we can pull it out of the integral. And when we integrate dt, we get t, plus, of course, the obligatory constant c. And we know the initial condition for the velocity, which is that the velocity at time 0 is equal to 0, which tells me that c is equal to 0. And I now have velocity of t is equal to a times t. I still don't know what a is, but that's not a problem. Since I have velocity, I can find position. And the reason I want to find position is that I'm given information about the position at a couple of different times. And I figure it's probably going to be helpful to me to find the position. So we have x of t is equal to the integral of at dt. Remembering that a is a constant, we pull a to the outside using the constant multiple rule, and appeal now to the power rule, giving us a times 1/2 t squared, again, plus a constant c1. And we are told that x of 0 is equal to 0. So we have 0 is equal to 1/2 a times 0 squared plus c1, where c1 is equal to 0. So winding our way at long last to the end, we find that x of t is equal to 1/2 at squared plus nothing. Well, how does that help us? Well, there's one piece of information that we haven't used yet, and that is the fact that when t is equal to 4, x is equal to 100. And so I can substitute those values in, and lo and behold, I have something, which is an equation that allows me to find a. A is equal to 200 over 16. Sorry, A is equal to 200 over 16, or 12.5. What kind of units do we have here? The units are going to be in centimeters per second, or centimeters per second squared. Now, if you're in physics, the temptation is going to be for you to appeal to physics equations. And I want to urge you to resist that temptation and instead to use the calculus method that I taught you here. And the reason for that is that the physics equations are predicated on the assumption that acceleration is always constant. In the problems that we worked on this page, and on this page, and on this page, the acceleration really was constant. But this is not always the case. In this particular problem right here, acceleration